All right, so understanding inverse relations can be kind of tricky. We did it a little bit in Algebra 2, but now we have to firm up our understanding and have a really solid hold of what an inverse function is and how they are manipulated, how you can move from one to the other, either algebraically or in a picture. So this is a little cutout, it's just right from your textbook. And if you look at the picture first, it's hard to see right in the beginning, but if I highlight some parts, hopefully you'll be able to see how one of these is a reflection over the red axis of another, or the red line of another. So the definition of an inverse relation is the inverse of any function is the function you get if you were to graph the original and then fold your paper across the line y equals x. And you can sort of see that right here. If I were to take just this arm, just this part of the blue graph, and imagine folding my paper right across that red line, then I would get this. I'd be able to trace this shape on the other side. So you can sort of see that that's on the other side of that fold line. So the same thing is true if I were to just take this part of it and imagine reflecting over, just folding the paper over, that it's easy to see how this would be the line you could trace, or the curve you could trace on the other side of that red line. And that's true all the way across both graphs. And you'll notice that these points where the initial graph intersects the line y equals x, nothing happens to them, because if I folded the paper they would just be in the fold and they would stay exactly where they are. So that's kind of a visual view of what a inverse is. Now let's look at a point-by-point view. If you look at the table, so the blue graph is the parabola y equals x squared minus 4, and the green graph is y squared equals x plus 4. That would be the inverse, or specifically the equation of the inverse, or the formula for the inverse. And so you can see here is the table for the inverse graph. Now if you look point by point, if -3, 5, so this is just a point, -3, 5, is on one graph, then on the inverse graph there must be the point 5, -3, where x's and y's have changed position, right? So input and output values reflect over that red line. And if we look at the -3, 5, we see it's this point for the blue graph, and that by reflecting over that red line I get the opposite point, and the coordinates for these points are exactly the coordinates that are listed here. All right, so let's go over to Desmos, and I've set up a graph. The dotted line, of course, is the line y equals x, and then we want to look at the inverse of the function y equals x cubed minus 2. And I'm going to do that by letting Desmos pick some tables or some values for me for a table. So I'm just going to open up my operations and I'm going to switch my graph to a table. So I still have x cubed minus 2, that's the same graph, but it's chosen some input output values for me. It's chosen a table. And let's look at now what I want to do is just create points that should be the inverse. So this point reflected straight over, I would expect to be -1, +1. And if I turn this point on, it's kind of obvious. I have 1, -1, so straight across that line I would get -1, +1. So I'm going to turn this off. For some reason when I'm making a video I get less control of Desmos. All right, so I want to plot those all of those points. I guess I can do it down here. So what did I decide? I needed -1, 1. Right? And look what happened. There it is. And then I'm going to plot another one. Let's go with, well, what should happen here? So this is the point 2, 6. So I expect to get 6, 2. 6, 2. So I expect to get this point over here. So if I put in 6, 2, that's the point I thought I would get. I don't know yet that that's on the inverse, but we're going to plot a few of these points and then I'm going to calculate the inverse and come back here. So let's do just this other one here, this last one here, which would, well, the intercept would be valuable. The intercept is at x equals 0, y equals -2, and over here you can see x equals 0, y equals -2 would be on the inverse. All right, and so, that's not exactly right. Y equals, 0, -2, that one's already, I didn't do the inverse. -2 and 0 right here. So, and notice that if I have a intersection point on one graph, then if I have a y-intercept on one graph, the inverse of it would have an x-intercept. That's kind of interesting to notice. So let's go ahead and calculate how to calculate the inverse of this function on our chalkboard and then come back and put the graph in and see if I indeed travel through all of these points. So this is y equals x cubed minus 2. So that's the picture that I have on Desmos. And if I'm asked to calculate the inverse of that graph, it happens to be a function, so I'll call it that. I'm asked to calculate the inverse. I'm going to take advantage of the fact that we saw in the table that on the inverse graph, x's and y's change position. -2, 0 becomes 0, -2. X's and y's change positions. So I'm going to calculate the inverse of this by plugging in x for y and y for x. When I do that, I can solve for y if I want. I could solve, sorry, that's a cube. I could say y cubed equals x plus 2, and then y equals the cubed root of x plus 2. I could use it in either form. Let's go back to Desmos and see if that tells us, if that gives us what we expect. Fingers crossed. So y equals the cubed root. I think I'm going to do it in this form. Y cubed equals x plus 2. I think Desmos will work in that way. So I'm going to ask for y cubed equals x plus 2. And look what happens. It goes right through those points. And I get exactly a reflection across that line. That's pretty cool that it works that way. So let's go back. And now I want to calculate as another example. So we finished that example. I've shown that if I graph a graph and then use the fold over this line, y equals x, I could trace the opposite. So if I have the green graph, I can fold over the line y equals x and then just trace the orange graph onto my paper from there. But I'm not always working with graphs and papers, and these days we're barely ever working with graphs on paper, so folding is really not an option. But I could plot a few points by just switching the input output. So what's an input output becomes, well, output input, even though it's an input output for the other graph. So, and then just sketch it out that way. But let's go ahead and graph or find the inverse. They've given us the inverse, but let's go ahead and show that that's true for this graph. So I'm going to calculate the inverse. Of y equals x squared minus 4. So again, taking advantage of the fact that on inverse graphs, x and y switch places, I'm going to put in x for y and y for x. And then I can first solve for y. Y equals, y squared, excuse me, equals x plus 4, which is exactly what they have. Or I could leave it just the way I started, which is x equals y squared minus 4. Either way, I've written an equation for the inverse of the original relation. All right, so that's enough chit chat. Let's do a couple of problems. If I'm given the function 2/3 x plus 2 and asked to find the inverse. So I'm going to go over here and look for the inverse. First thing I want to do is switch out the variable. So x equals 2/3 y plus 2. And then I want to solve for y, because even when it's an inverse, we want to have x variables as a function of y. So I have 2/3 y equals, sorry, dog's walking around on the bed. 2/3 y equals x plus 2. Okay, and then I'm going to multiply both sides by 3/2. So y equals 3/2 times x plus 2, which is the same thing as 3/2 x plus 3. So I'm saying, and in fact I'm not really positive I'm right because I haven't worked this problem before, but I'm saying that this function is the inverse of this function. Now, how would I check to see if it's true? Well, that's kind of cool, because since the inverse reflects over this line y equals x, they sort of undo each other. Like all the stuff happening on the upper side of that line happens over here on the other side. And if you could imagine adding them together, they would sort of disappear each other, because it's a complete reflection. It's like matter and antimatter, right? They just undo each other. They would kind of disappear each other, which is just an idea. So let's see what happens if I make a composition out of the two functions. So let me be explicit with that. I'm going to call this time f of x equals 2/3 x plus 2, and then I'm going to call g of x, the inverse, equals 3/2 x plus 3. Okay, so if I compose these and take the f of g of x, then I get 2/3 times g of x plus 2. Now put g of x inside, 3/2 x plus 3. Okay, so that is 2/3 times 3/2, that's just x. 2/3 times 3, well, that's just 2. Well, I almost erased my mistake so you wouldn't know I made one, but this is actually perfect because it says x plus 2 plus 2. You don't know why yet necessarily, but I'm going to tell you that this shows that I did something wrong. So let me come back over here and look at my work. And you probably saw it when I did it. 2/3 y equals x minus 2. This is a minus 2. So 3/2 x minus, cancel the 2's, minus 3. Now let's come back in and try it again. So this is a minus 3, and this I'm going to just erase and start again. So 2/3 times 3/2, that's just x. 2/3 times negative 3 is a minus 2. I've got a plus 2 here. Those cancel, and so I get x equals, well, this being a y value, right? It's just a function that we can write as a function, or we can write it as y notation. The composition function y equals x. And look at this. How cool is this? That's actually the diagonal line. And so when you compose inverses of each other, you end up with y equals x. They just disappear each other right into that diagonal line. So you can always check your work when you calculate an inverse, because if you don't end up with the y equals x, as I did not right here, you have to go back and find your mistake. I found my mistake. So now I can say that it is therefore y equals 2/3 x plus 2 is the inverse of y equals 3/2 x minus 3.